So let us start the lecture by recalling that in the previous lecture we had started looking at the notion of divergence of a vector field. So let us recall, given a vector field F, the divergence of the vector field is defined to be a scalar field. So divergence of F is partial derivative of the first component of F with respect to x plus partial derivative of the second component with respect to y plus the partial derivative of the third component with respect to z. So this gives us a scalar field which is called the divergence of a vector field, and we had seen that this arises in fluid flows and in writing the analyzing the motion or the flow of a fluid. Let us look at some properties of this, but before that let us state that though our definition depends on the components of the vector field F, we are looking at the components F1, F2 and F3, so it seems the definition depends upon the choice of the coordinate system, but that is not the case. One can prove it, but we will not do it here at this stage. But it's good to observe that the definition of divergence of a vector field does not depend upon the choice of the coordinate system. Symbolically, like we represented divergence of a vector field in terms of the operator del by del x and so on, so similarly we can represent symbolically the divergence of a vector field as follows. So it is represented as del dot f, where del is the operator that we have already defined, partial derivative of x with respect to x, I partial derivative with respect to y, j plus partial derivative with respect to k. So we treat this as a vector. F is a vector field with components f1, f2 and f3. So if we take this dot product treating these as vectors, then that comes out to be partial derivative of f1 with respect to x plus partial derivative of f2 with respect to y plus partial derivative of f3 with respect to z. That is a divergence, because I dot I only survives, I dot j is 0, I dot k is 0 and so on. So we can treat them as vectors and write symbolically divergence to be del dot f. This is useful in many computations, so we will see it soon, some applications of this. Another way of representing the divergence is the following. We can write also this as summation, because there are three terms, right? So we will also write it as summation I dot del f by del x, or it is also written as the operator is taken inside I del f by del x dot f. So this is another way of writing the divergence of a vector field. So let us look at some properties of this divergence. How does divergence behave with respect to addition of scalar fields, scalar multiple of scalar fields, and so on. So the first property, let us look at f and g be two differentiable scalar fields, and u and v and w are differentiable vector fields. Then the first property says that the divergence of k times v is equal to k times divergence of v. Like ordinary differentiation, the k comes out from the operator divergence. And similarly, divergence of v plus w is equal to divergence of v plus divergence of w. So these two properties together say that divergence is a linear operation. And the proof is easy to, these two statements are easy to prove, because for v, if you take the components v1, v2, v3, then divergence of k times v is, we are going to look at the partial derivatives of v with respect to of the first component, that is k v1 with respect to x. So k will come out. Similarly, when you take the second term, that is the partial derivative of k v2 with respect to y, that comes out. So k comes out, because there is only the differentiation of one variable at a time being taken. Partial derivative of with respect to x, partial derivative with respect to y, partial derivative with respect to z. Similarly, differentiation being a linear operation, this property also holds. So these two properties are easy to verify. Let us look at the next property, which says if you multiply a vector field v by a scalar field f, then what happens? Now it behaves like differentiation, the product rule. So it says the divergence of f times v, where f is a scalar field, v is a vector field, is equal to f times divergence of v plus v times, now v is a scalar field, so differentiation means it is a gradient of f. So this is a formula for product rule for divergence, where f is a scalar field and v is a vector field. So let us prove this using our symbolic notation. Divergence of Fv is equal to summation I dot partial derivative of with respect to x of the vector field. The underlying vector field is there is f times v. So now the partial derivative of Fv with respect to x, there is a differentiation of one variable only. So that behaves like product rule. So this becomes equal to I dot this partial derivative with respect to x gives me two terms, is partial derivative of f with respect to x times v plus f times the dv partial derivative of v with respect to x. And now I can split these two into two different sums, and that is equal to I of fx dot v, because only fx is going to be part of the summation, v is independent of sum. So we regroup this as I fx dot v, and here f is a scalar which is independent of the sum, which comes out. So it is I dot del v by del x, that is divergence of v. So this is what the formula says, f dot divergence of v plus v times gradient of f. So that is the formula for the product of a vector field by a scalar field, the divergence. So there you see that the main thing is how the symbolic representation of divergence helps us to prove this formula. Let us prove another formula using a same relation. The divergence of f into gradient of g is equal to the expression on the right hand side. But this follows from the previous one. What we have to do is we have to just write instead of v the gradient of g, and that will give me the formula. And here this del square is the operator partial derivative with respect to g, second order partial derivative of g with respect to x, second order partial derivative of g with respect to y, plus second order partial derivative of g with respect to z. So which is an important operator used in partial differential equations called Laplacian of g. It appears in many places, we will see it later on. So to prove this, we had to only substitute in the previous formula v equal to gradient of g, and that it follows from there. So we don't do much about it. Next, we want to analyze how does divergence behave with respect to the cross product of two vectors. So let us take two vector fields v and w, and we want to know if we take the cross product and take the divergence of that, can we write in terms of the individual vector fields? And the formula says this can be written as I cross, see earlier we had I dot, now it comes I cross partial derivative of w with respect to x. So this is a vector dot v minus partial derivative of I cross partial derivative of v with respect to x. This is a vector dot w. But keep in mind this is three terms, okay? Summation means there are three terms here. So let us try to prove this. Let us prove this formula. So we'll do it symbolically. Divergence of v cross w, once again we'll write it as del dot v cross w, okay? And for v cross w, the symbolic representation of this is summation I dot, okay, divergence, so it is dot v cross w, partial derivative with respect to x of v cross w. And now here once again we apply the product formula for differentiation. It is differentiation with respect to one variable only. So that gives you two terms, the partial derivative with respect to v of x cross w, keeping in mind what is the product here, is a cross product coming here, plus the second term is v cross product partial derivative of w with respect to x. So this is what it comes out to be. We have simply written the symbolic way of representing the divergence and use the ordinary differentiation rule, product rule, to write these two terms. And now these two terms can be written separately. So this gives us, this is equal to I dot partial derivative of v with respect to x cross w plus I dot partial derivative of v with respect to w cross partial derivative of w with respect to x. So these two terms summation splits. And now this we want to split this. Aim is to write this formula of divergence of v cross w in terms of the individual vector fields. So to do that, what we do is the following. We compare the notion of the scalar triple product. So it is a dot b cross c, and similarly here it is a dot b cross c. So for that, what we'll do is use that formula of a dot b cross c we can shift around the dot and the cross product. So we'll use that. So we'll write as I. So I cross the first term, that is partial derivative of v with respect to x. So a dot b cross c is a cross b dot c. So that formula is being used, and so using that we get the required expression. So keep in mind, so let us just recall what we are saying, that let us go back and look in this formula. So it is divergence of v cross w, right, is a product. V cross w is a product, and it says, see, normally in a product rule you will expect plus sign, but this is an exceptional thing. Here a negative sign is coming, so it says it is this vector dot v minus this vector dot w. So and what is this vector? Let us understand this vector. What is this vector? So let us expand this vector and see what it is. So this vector I cross del v by del x, right? Let us understand. So it is summation del v by del x is partial derivative of v1 with respect to x I plus partial derivative of v2 with respect to x j plus partial derivative of v3 with respect to x k. Now this is a cross b plus c plus d. So we can use the distribution of the cross product over addition, and we can write this as, right, so I cross I, that will give you 0, I cross j will give you minus sign, and I cross k will give you a minus of I cross they will give you minus of j. So I cross j is equal to k, and I cross k is equal to minus of j. So using this when we expand these terms, we get the following partial derivative. This thing is nothing but partial derivative of v3 with respect to y minus partial derivative of v2 with respect to z of I. So the first term, the third, right, the partial derivative with respect to y and partial derivative with respect to x. So z, x term is missing. Similarly in the second one, it is partial derivative with respect to z and partial derivative with respect to x. The y term is missing. And similarly in the third one. So this vector is nothing but this vector. And this vector plays an important role in many physical applications. So we'll try to give it a name so that we don't have to write every time this thing again and again. So let us make it a definition. For a vector field V with components V1, V2 and V3. So V is a vector field with components V1, V2 and V3. Its vector, so for this vector field, we define a new vector field called curl of this vector field. So given a vector field, we are getting another vector field called curl of the vector field. So this is a vector field on the same domain and is defined as follows. So the first component of this is, as we got earlier, this one, partial derivative with respect to v3 with respect to y, or partial derivative of v2 with respect to z, this difference I, the first component. Similarly, this is the second component and this is the third component. So is the difference of the partial derivatives. For the first one is the difference of the partial derivative with respect to y and z of v2 and v3, and similarly the other one. This is what is called the curl of the vector field. And we'll see applications of this soon. So symbolically, like the divergence was written as del dot v, we write the curl of a vector field as summation I cross partial derivative with respect to v of x, or also is sometimes convenient to remember this, or for computation purposes write this as a determinant. So for the curl v, right, we want to find the components. So I, j and k, partial, this is a differential operator, partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. V has got components v1, v2, v3. So consider this determinant and expand. So what it will give you? I times this goes, partial derivative of v3 with respect to y minus partial derivative of v2 with respect to z. That will be the first component. Similarly for the second one, minus times partial derivative with respect to v3 of x with respect to x, and partial derivative of with respect to v1 of z. So that will be the second component, and similarly the third one. And that is precisely the curl of the vector field v. So we can write curl of v to be equal to, treat as if this del is a vector and v is a vector, and you are looking at the cross product of these two vectors. So curl v is also written as del cross v. So we got three things now. For a scalar field, we write divergence. It is del of f. For a scalar field f, we write del f. For a vector field v, the divergence is a scalar field which is del dot v, and for a vector field v, the curl is a vector field again which is written as del cross v. And once again, let us point it out how the notion of curl is defined with respect to the components of the given vector field v. It is independent of the coordinate system that you use, which can be proved, but will not do it at this stage. We'll assume that one can do it. That the definition of divergence curl is independent of the coordinate system. Let us look at some examples to illustrate this point. So let us look at examples. For the rotation of a rigid body about an axis through the body, the velocity vector at a point P. So imagine a body is rotating is rotating about an axis, and that axis is passing through the body. Okay, and P is a point on the body. So we saw that the velocity vector v of this body is given as w cross r. Okay, where w is a vector. Do you recall that? So recall, this is a body which is rotating, right, and there is an axis passing through it. So and it is rotating like this. So we had a vector w along this whose magnitude was equal to the angular velocity of this body, and for a point P at a distance r, this is say origin and this is r. So we saw that the velocity vector is given by the following. So velocity vector at a point P is given by w cross r of P, where w, as I said, is a vector along the axis with the magnitude equal to w, and r is the position vector of the point P. So that is what we just now said. Right? Okay. So if we take that, now imagine this axis of rotation. Let us imagine this axis of rotation is my z axis. So let us say this is the z axis and here is the origin. Okay. So in that case, this position vector, this velocity vector v, can be written in terms of it is w cross r. So for this w, this point, okay, this is r. We can write down what are the components and we can compute. So there is I, j and k. It is w cross r. W will have components 0, 0 and w. This is the velocity is w. And the position of a point is x, y and z. So this w cross r, the velocity of a rotating body at a point P with the position x, y and z is given by w times minus yi plus xj, where the axis of rotation is taken as the z axis and w is the angular velocity. So we can write down, let us look at the curl of this velocity vector. The curl of this velocity vector will be given by, so this is I, j and k, partial derivative with respect to x, y and z. So this will give you minus wy plus wx from here, and third component is 0. So that is 2 times the vector w. So, and w is the vector whose magnitude is the angular velocity. So this says that if there is no rotation, right, then this w will be equal to 0, angular velocity is 0. So no rotation means curl of v is equal to 0. So in that sense, curl signifies the rotational tendency of a vector field. So that is what we say, curl of z is 0 if and only if v is equal to 0. So that is the tendency of the vector field to be irrotational. So one defines that for a vector field v, we say it is irrotational if curl of that vector field is equal to 0. So you see that curl is a vector, is a curl of a vector field signifies a physical property of something being tendency of being rotational or irrotational or non-rotational. So let us look at some examples to illustrate this point. Let us look at a vector field fxyz, which is given by 2xi plus x square plus z square j plus 2zy of k. So this is f1, this is f2, this is f3. So what will be the curl of this? to compute the curl of this vector field, we write down the determinant. So curl of the vector field will be equal to I, j and k. The second row is the differential operators, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z of 2xy, x square plus z square and 2z square. But if you look at xy, we have to differentiate this with respect to, so when you want to differentiate, so this with respect to y minus this with respect to z, so that is 2z minus 2z, that is equal to 0. And similarly other components, when you compute, this comes out to be equal to 0. So this says this vector field is irrotational. Let us look at another way. Let us look at a vector field which arises as the gradient of a scalar field. So such vector fields, as we have seen, they are called vector fields with a potential function. So potential is the function small f. So let us look at a vector field capital F whose potential function is small f. That means what? That means f is equal to gradient of the function small f. So in that case, let us compute what is the curl of this vector field. So the curl of this vector field will be given by I, j and k, the differential operators, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Now what are components of f? Is the gradient of a scalar field f. So what are the components? So partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. Now let us compute what is the determinant. So the first component of I, this row, this column goes, so it's partial derivative with respect to y of partial derivative of f with respect to z. So this is nothing but the second order partial derivative of f with respect to z first and then with respect to y, minus partial derivative of f with respect to z and then with respect to y. So you see that the order of differentiation in the two is reverse. Here is you taking first partial derivative of f with respect to z, right, and then with respect to y, and here you are taking with respect to y first and then with respect to z. So that is a component of I. So if you write down that, so this is what you will get. This is the curl of the vector field, which is the gradient of a scalar field f. You see that if you recall, we said that if f is such, it is so that its partial derivative, it is twice continuously differentiable, then the mixed order partial derivatives are equal. So under that condition, this will be 0, this will be 0, this will be 0. So then we get an example that if a vector field has a potential small f which is twice continuously differentiable, then it is irrotational. So every vector field which has a potential is irrotational. So we are putting that condition, though it is not specifically stated here, that the potential function should be twice continuously differentiable. So that is irrotational. So let us look at some animations of this curl. How does the rotational tendency appear in looking at? So this is the vector field we are looking at, minus yi plus xj, right, and its curl is equal to 2k. So you see it shows that if I take a part of the domain which looks like rectangular, it will keep on rotating, right. And similarly, we take another vector field which is x minus yi plus x minus yj, then again it has rotational tendency. You can see that if I take a small piece of that, it rotates and goes off. Next, let us look at a vector field which is yi minus sin x. So some periodicity is being introduced in the second component. Its curl is equal to 1 plus cos xk, and you can still see that there is some rotational tendency in this vector field. So as the things appear, it keeps on rotating. Of course, the rotation goes somewhere else, but there is a rotational tendency in this vector field also. So this is how the curl appears when you want to look. So f is a vector field. This could be, for example, the force field. F is a force field of something, and you want to know how this force changes, or f could be the velocity of a fluid flow, and you want to know how does the fluid flow appears, how it will affect a a rectangular piece in the domain. So this is how the curl appears. Okay, so this is a view of curl saying, indicating that what a rotational thing means. Like we had studied divergence with respect to various operations of addition, scalar multiplication, and dot product and cross products and so on, and we have studied divergence, how does it behave with respect to these operations. We want to study similarly the curl also with respect to these operations. So this is what we are going to do next. We are going to study the properties of the curl with respect to various operations on vector fields. You have two vector fields, you can add the vector fields, you can multiply a vector field by a scalar field, you will get another vector field. So, and you can take cross product of two vector fields, you will get another vector field. So how does the curl of this new vector fields appear with respect to the earlier vector field? So this is what we want to analyze. So the first property says curl of the sum of vector fields is equal to sum of the curls of the respective vector fields. That seems very nice. It goes very well with our earlier sort of a conception of differentiation being a linear operation. Okay, so the first property says curl of u plus v is curl of u plus curl of v. So how do we prove it? So proofs of all these things are going to be done using symbolic representation of curl and so on. So symbolically, curl of u plus v is the cross product of sigma I cross the vector field, which is u plus v. Now here we use the property of a cross b plus c is same as a cross b plus a cross c. So it splits into two sums, and these are the two sums, and this is nothing but the curl of u, and this is nothing but the curl of v. So that property is easy to verify, which is using the symbolic representation of the curl. Right? So let us look at a next property, which is curl of a vector field u multiplied by a scalar field f. So when you multiply a vector field by a scalar field, you will get again a vector field. So it says curl of this new vector field can be written as, like ordinary differentiation, it behaves like f times curl of u plus, for f the differentiation appears in the form of gradient of f cross u. So this is like the product rule, behaves very nicely. And once again, to prove this, we just use the symbolic way of writing curl. So curl of f times u is nothing but sigma I cross, right? For curl is a cross, partial derivative with respect to x of the vector field, and the vector field is f times u. So now once again we use the product rule for differentiation of function of one variable. So this product splits into two parts, and that gives us I cross partial derivative of u with respect to x plus partial derivative of f with respect to x times u. So this becomes I cross sum of these two things, and once again using the distributive property of the cross product over the sum, this splits into two parts and gives you I cross f partial derivative of u with respect to x plus I cross partial derivative of f with respect to x of u. And now let us understand here this in this first term, f is not appearing anywhere. F is independent of the summation things. Summation is over I or x. So this f can be taken out. And now to do the same thing here, we have to do some understanding. So this we can push it inside here. So it is a scalar. Okay. So we can write it as I partial derivative with respect to x of f cross u. So let us write that the two things separately. So the first one, f comes out. So it is summation I cross partial derivative of u with respect to x. And here this is a scalar, so we take it out, partial derivative of f with respect to x, but still x is there, so it will remain inside summation. I can't take it out. So this comes here, and it is I cross u. So this becomes is a part of the summation cross u, and f, this is the part of the summation, and this is the curl of the vector field u. Okay, so this is f times the curl, and this is nothing but the partial derivative of f with respect to f cross u. So that we can write in terms of so f times this is curl of u, and this is the gradient of f times cross u. So ordinary product rule kind of thing happens here. So finally let us analyze how does curl behave with respect to the cross product of two vectors. So we are looking at two vector fields u and v, and we want to look at the curl of u cross v. So now this is the most important, or not really important, but is comparison with the ordinary differentiation of the product things fails here. So you would expect curl of u cross v to be having something like the ordinary one function at a time and differentiating the other. So sum of two terms or three terms or something, but it totally defies that law, that kind of a conception. So one should be careful as far as curl is concerned. So it says curl of u cross v is nothing but v dot del u minus u dot del v plus this expression. And it's not easy to remember this kind of a formula. Only one can compute, but the idea is that curl of u cross v is written in terms of independent vector fields u and v. Right? What is v dot del and what is u dot del? There is something new which has appeared. So let us explain that v dot del is a symbolic thing for writing summation I dot v partial derivative with respect to x. So this is an operator. Okay, this is being applied to u and this being applied to. So this is a partial derivative, right? In terms of this. So this is I dot v partial derivative with respect to x, and similarly with respect to. So to prove this, once again we will do the method of proof is same as that for other things. We will use the symbolic representation. But so as I said, you would have thought a cross b cross c, right? Normally the formula is this, where a dot c b minus a dot b c. So two terms are there with a negative sign. Here it comes out as four terms, two with negative and two with positive. So it's a difficult thing to remember. Only one can compute and see. So computation, if we do logically, it's not difficult at all. So we'll do that. So we'll write curl of u cross v. Okay, as symbolically it is I cross partial derivative with respect to x of u cross v. Now we proceed as before. This is derivative of function of one variable only. So this behaves like ordinary product. So this splits into two parts. So partial derivative of u with respect to x cross v plus u cross partial derivative with respect to x, and then we'll split the two terms. So this by product rule is equal to this, and now split these two terms to get I cross partial derivative with respect to x. So this sum plus this sum. So this is what we get by using the symbolic representation for the curl and using the fact that the differentiation with respect to one variable of the cross product behaves like ordinary product rule. And now here what we are going to do is we are going to use the formula for the triple cross product a cross b cross c. This is also a cross b cross c. So we'll use the triple product formula that a cross b cross c is equal to a dot b c minus a dot c b. So we'll use that. So this will become a difference of, so this is the formula for the triple cross product. So we use it here. So this will be a difference of two terms and this will be a difference of two terms. So what will be two terms? So it is a dot, so I dot v cross this plus I dot u cross that. So let us write those two terms. So these are the four terms that you will get using the formula for the triple cross product. And now the first one, okay, we want to write this I dot u partial derivative with respect to x, right, minus. So let us split this into four different terms. The first one, see, partial derivative with respect to x, u. So we write this u separately out and remaining inside the sum. So that is what it appears. Okay, because I is going to vary and x is going to vary. Similarly, I is going to vary and x is going to vary. So is I dot partial derivative with respect to x of v. So that is the second term here. Okay, and minus. So this is a extra thing here. This u is not there, so no, this u is there, sorry, this u has appeared there. Okay, right. And then the next one is I dot partial derivative of v with respect to x of u. Okay, so this is taken together, right, and v is written out and u is written out because that is not going to affect. And finally the fourth one, I dot summation I dot u, right, of partial derivative of v with respect to this thing. So that is the last thing here. The one term which has gone out is missing, that is v here, actually outside. So this can be summarized as follows. Okay, so this is just it's difficult to remember, difficult to sort of justify or analyze this analytically. The best thing is this is not a very useful formula. It is just you can treat it as an exercise in writing symbolically things. So once we compute, one hardly uses this formula. One computes the curl of the cross product of u and v, and then it computes the curl. Okay, so this is the property of the curl with respect to the cross product. So what we have done till now is we have tried to analyze how various vector fields and scalar fields arise in practice. So we started with one scalar field and then looked at the divergence of a scalar field, and we saw that divergence from a scalar field, this gives you something called a vector field, which is called the gradient of the vector field. And this gradient we saw appears in many examples also. Then looking at a vector field, we looked at a concept called divergence of a vector field, and we saw that divergence appears in studying fluid flows. And then we looked at, given a vector field, something called curl of it, which is again a vector field, which appears in analyzing rotational tendencies of vector fields. So this is how various scalar fields and vector fields arise in many physical quantities. Right? So we will be using these things later on in our analysis of vector fields and scalar fields. So now we are going to study special vector fields, which are functions defined on intervals in the real line and taking values in R3. The physical motion for physical intuition for studying such kind of things comes from, imagine a particle is moving in space and you are locating its position at different time points. So time is a part of the real line, it's part of an interval, say A to B. So the particle starts moving at time t equal to A, and you note down where it is in space. So the position at time t is going to be determined by three vectors, namely component xt, yt and zt. So that is a point in space. Okay, so as time moves, the particle moves in space, and that position is recorded, and that is called a curve in space. So let us define. So this is a part of the interval, okay, A to B. At any point t, you get a point in space. So that is the position, and as the time moves, you get the particle moves. So mathematically, this can be defined as a function taking values in. So there is a function taking values defined on a set in the real line, interval in the real line I, taking values in R2 or R3. Okay, so if the values are in R2, you say this is the curve in R2, or you say it is a plane curve, and if the values are in R3, you say it is a space curve. So plane curve and space curve. But at this point, one should be slightly careful that, okay, before that let us just give some more notations. The starting point A, the position is called the initial point, R of A is called the initial point, and R of B, the position at the time B when it stops moving, that is called the final point of the curve. Okay, and look at the trace of this particle is a position in space. So as the particle moves in space, you are going to get a curve, right? You get a position. So look at the graph of this function, that is called the path traced by the curve. Now let us be very careful that a curve is a curve is a function from interval to R2 or R3, and path is the image of this function. Okay, so it is something like, you can think like a train moving on a track. So the train is the curve where the track is the path, right? So that is the image. On the same path, you can have two different trains moving with the same initial point and same final point. One can write in components the curve to be equal to xti plus ytj plus ztk, because rt is a point in space, so it has component xt, yt and zt. Okay, so this is called a parameterization of the curve. So a curve is with the parameterization, and the image is the path of this curve. So one also writes a curve in this fashion. Let us just look at two examples of this. So for example, look at the curve with the rt equal to t, t and t. So at time t equal to 0, r0 is equal to 0. So it starts at origin, and as you move, it moves to the point t, 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 and at the end point is 1, 1, 1. So you can see this is a straight line. So the path of this path is the straight line which starts at 0 and goes up to 1. So this is a line segment starting at 0 and going up to 1. So this is the curve. But the same curve can also be given a different parameterization. I can define this path in another way. So we'll do that. Okay. So for example, look at the function which is t square I, t square j and t square k, still t between 0 and 1. So still you can see that the image of this curve also is the same straight line, but the formula or the parameterization is different. So the basic idea is the same path, same curve, right? A path can be the image of two different curves. Okay. Thank you.